Hello, and welcome to our video on acid-base theories, as well as Kw. So we're going to begin with the simpler of our two acid-base theories, and that's known as the Arrhenius theory. And the Arrhenius theory states that acids are going to be anything that produce hydronium ions when dissolved in water. So our acid plus H2O are going to react to form hydronium, and we also make another ion as well, an anion, and we'll talk more about this anion later in the video. So let's take a moment to talk about Arrhenius. That's this gentleman over to the right here. He was an exceptionally brilliant man. And so not only did he come up with acid-base theories, as well as did pretty amazing research about rates of reactions, but Arrhenius also was one of the first people to sort of publish theories about how carbon dioxide affects the climate. And so his research centered around ice age cycles on Earth, but it really kind of laid the groundwork for the modern understanding of CO2 as it affects climate change and global warming and such. So brilliant, brilliant guy. And that work around CO2 was done in 1896, I think, so very long time ago. Moving on to bases, the Arrhenius theory states that bases are going to be anything that produce hydroxide ions when dissolved in water. So acids make hydroniums, bases make hydroxides when we dissolve them in water. So now we're going to move on to a slightly more general theory of acids and bases. So Bronsted-Lowry theory states that acids are going to be anything that donate protons. So I want to point out this theory doesn't conflict with the Arrhenius theory in any way. It's just more general. It applies to more situations. And so what it states essentially is acids donate protons, and if we happen to donate protons in an aqueous solution, those protons will react with the water molecules to make hydroniums. So just like the Arrhenius theory predicts, we can make hydroniums from these acids, but the Bronsted-Lowry theory says, well, we don't really have to be in water, and maybe we could have a different solvent, or maybe we could have a gaseous mixture. Anything that's a proton donor is an acid, and that may, of course, include forming hydronium ions. And the Bronsted-Lowry theory of bases states that bases are going to be anything that accept protons. So again, this is more general than the Arrhenius theory. It doesn't conflict with it. The Arrhenius theory, says that bases make hydroxide ions, and hydroxide ions are great proton acceptors. But this Bronsted-Lowry theory comes along and says, yeah, hydroxides are great bases, but there's lots of other bases, and really anything that accepts protons can be a base. And so here we have the example, if we take water and we react it with ammonia, we're going to form ammonium ions as well as hydroxide ions. So this is really a base by either definition, because we're making hydroxide ions, but if we look at it by the Bronsted-Lowry definition, we can see that our ammonia is going to accept protons to form ammonium. That's how we know it's a base, and our water actually donates a proton. It acts as an acid right here. So water is unusual. It can act as either an acid or a base. I'll be talking about that more later on in the video. But for now, what I'd like you to do is please pause the video and complete questions 1 through 4. Welcome back. So let's talk a bit about strength of acids and bases. So strong acids are going to be acids that completely ionize in aqueous solutions. So in other words, if we take a strong acid, any strong acid, and we dissolve it in water, we're going to end up with complete conversion to form hydronium ions. And so there's only actually 6 common strong acids. And so those 6 common strong acids I've written down right here. You're going to want to remember those or commit those to your note card. And it's handy because any other acid you encounter that's not on this list, you can pretty safely assume is going to be weak. And one of the giveaways that you have in acid is you'll usually see the term acid in the name if you're given the name, or if you're given the formula, you'll notice that these are a bit unusual because hydrogen is listed first. So the majority of compounds that have hydrogen listed first are actually going to be acidic. So just a handy piece of useful information right there. And so our weak acids only dissociate slightly in water. So we have a reversible reaction, in other words. So notice our reversible reaction arrows. So how can you tell if an acid's weak? Well, one way is to look if it's on that list of strong acids, and if it's not, it's probably weak because most acids are weak. The other way is if you're given the chemical equation, generally you'll see that they'll use these reversible reaction arrows as opposed to the type of arrow we used up here in the slide. So again, weak acid, it's not in our list of strong acids, and we have these reversible reaction arrows. So what's the difference in solution? Well, we have two bottles here. One's a 1 molar or 1 mole per liter solution of HCl. And what we see is we have a lot of chloride ions in solution. So our HCl has completely dissociated, completely broken down to form hydroniums as well as hydroxides. And we have no remaining HCl's in solution. This is what we mean by 100% dissociation or 100% ionization. We've completely converted into hydroniums, and as a result, we have a ton of hydroniums in solution. Now, if we look at the same concentration of a weak acid, in this case acetic acid, which is the active ingredient in vinegar, most of the acetic acid molecules have just stayed together as one unit. So most of these do not dissociate. We have only a small amount of hydronium. So that's what makes one acid strong and another one weak. The HCl, if we have 1 mole per liter solution of HCl, that's going to completely break down and form a lot of hydroniums, versus that same concentration of a weak acid actually forms very few hydroniums because only a small percent dissociates, and so it ends up, as a result, being less acidic. So here's our list of strong bases. Again, most bases are weak, and so if you encounter bases that aren't on this list, you can safely assume them to be weak. And so you'll see the list right here, but also I like this list right here. You can choose to use either one. And group 1A and 2A metals combined with hydroxide ions are generally going to be strong bases, and for our purposes, most other bases will be weak. So let's talk actually about conjugate acids and conjugate bases. Right here we have a reaction of HF with water. This is a weak acid, and we can tell either by looking at our list of strong acids and seeing it's not listed, or by checking out the type of arrows that are used here, because we have these reversible reaction arrows right here. So we dissociate to some degree to form hydronium and fluoride. So if we look at the left side of our equation, our HF is our proton donor, so we call that our acid. And the H2O is our proton acceptor in this case, so we're going to call that our base, and then we're going to form the hydronium and the fluoride. But you'll notice that from our arrows here, we can clearly see that we're able to go in the left direction as well. And if we go in the left direction, what's going to happen is our hydronium is going to donate a proton to our fluoride. And so in other words, we've made a new acidic material on the right side of the equation we're going to call our conjugate acid. That's our new proton donor on the product side. We've also formed a conjugate base, which is our new proton acceptor on the right side of the equation. So acid and base are on the left side of the reaction like this, and the conjugate acid and conjugate base are on the right side. And so we see an interesting trend here that's going to be important later in the chapter, and that is the stronger the acid, the weaker the conjugate base. So in other words, if we look at a really strong acid like HCl, for instance, what allows the HCl to completely dissociate is the fact that those chlorides just give up those protons, they don't take them back. Now, on the other hand, the weaker the acid, the stronger the conjugate base. So if you look at a weak acid like HF, for instance, you'll notice from that previous page that our fluoride ions actually take back protons, and that's what drives our reaction again in that reverse direction. And so this is the trend we see. The weaker the acid, the stronger the conjugate base. In other words, the more the conjugate base takes back protons, driving that reaction to the left, or the less protons will release into solution. So I'd like you to pause the video and please complete questions 5 and 6. Alright, welcome back. Let's talk about our last topic of the day, and that is ionization of water. So what we see is water is actually able to react with itself to form hydronium and hydroxide, meaning that some water molecules are going to act as acids, as proton donors, and some water molecules as bases, proton acceptors, in order to form hydroniums and hydroxides. And you'll notice this is a reversible reaction. So what we're going to see, though, is the degree to which this happens is actually really, really small. So we talked about in the previous chapter, the smaller the value of K, the smaller the value of K, the more the equilibrium favors the left side or the reactant side. So we've written an equilibrium expression right here. So the liquid waters are left out, and all we're actually left with is the aqueous ion. So here's our equilibrium expression for that dissociation of water. So Kw, which is a constant, equals hydronium concentration times hydroxide concentration. And in a neutral solution, these are actually equal to each other. They're both 1.0 times 10 to the negative 7th moles per liter. So a neutral solution, again, will have equal concentrations of hydronium and hydroxide. But our Kw values down here, it's tiny, 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 10 to the negative 14th. So that tells us that our solution, that our amount of ions that we form is very, very small. Our equilibrium strongly favors this left side here. So we have almost entirely water and only a tiny, tiny amount of our hydronium and hydroxide. So again, in pure neutral water, so not acidic or not basic, the concentration of hydronium and hydroxide are going to be exactly equal to each other. But if we have an acidic solution, what's going to happen is that our concentration of our hydronium goes up and our concentration of our hydroxide goes down. So why is that the case? Well, the product of these two numbers still has to equal that same Kw, that 1.0 times 10 to the negative 14th. So if one value gets bigger, the other one must get smaller in order for them to multiply out that same constant. And in a basic solution, we see the opposite. In the basic solution, we end up with more hydroxide and less hydronium. And again, that's because the product of these two concentrations must equal that same Kw value. And so one of the things you'll be asked to do is calculate the concentration of one of these ions versus the other. So here we have an example question. What is the concentration, remember these brackets mean concentration, of a solution of hydroxide, what is the concentration of hydronium if the concentration of hydroxide is 5.0 times 10 to the negative 8th moles per liter? So we're going to plug this into our trusty Kw equation once we rearrange it. We're asked to solve for hydronium, so we're going to shift our factors around, and here we go down here. So here's our rearranged equation. And then we're going to plunk in our numbers. So Kw is a constant that'll be given to you on a quiz or exam. And we're going to plunk down our concentration of hydroxide right there, and we end up with 2.0 times 10 to the negative 7th moles per liter. So congrats, you survived the video. Please complete questions 7 through 12 now.